Yeah, so my name is very long, and the introduction really helped, so thank you, Dave. So today I'll be presenting my work on software-defined prober, which I did during my internship at AT&T Labs Research. This is done in collaboration with my mentors, Yaron, Kanza, and Balachander, Krishnamurthy. So persistent delays in networks are common, and they cause adverse effects on the network. So therefore, delay measurements need to be conducted constantly to detect these persistent delays. However, there is a trade-off between the measurement cost and the detection time to detect these persistent delays. If the measurements are done too often, the time taken to detect such persistent delays reduces, but the cost incurred to conduct such measurements is very high. On the other hand, if the measurements are conducted infrequently, the cost reduces, but the time taken to detect the persistent delays increases. So the network operator needs to find a balance between the measurement cost and the detection time. One such way is to bound the measurement. So a network operator could define a lower bound which specifies the minimum number of measurements which needs to be done on a link. So this provides a guarantee that a particular persistent delay will be detected under a given interval of time. And he or she could also define an upper bound which limits the total number of measurements which could be done on the particular link. Existing tools which is used for measurements such as ping and traceroute cannot apply such bounds. The main reason being such tools depend upon the underlying routing algorithm which is inflexible. So therefore, if it is required to find a set of paths which satisfy the particular constraints, it's going to be extremely hard and also will be expensive in terms of the number of packets being sent. So we present software-defined prober, which allows an adaptable and an efficient delay measurements in networks with such bounded constraints. SDProber uses probe packets to measure delays on individual links, and probe packets in SDProber take a random walk in the network. So SDProber is able to control the way the probe packet moves in the network by adjusting the weight in the graph. So by taking a random walk, SDProber avoids this complex set of computations to get to know the paths which will satisfy the constraints. SDProber changes the weights to satisfy the constraints. So SDProber increases the weights on links whose lower bounds are not satisfied, so that more probe packets goes to that particular region. On the other hand, SDProber reduces the weights on links whose upper bound is already satisfied, so that less probe packets go there. SDProber consists of three main components. First is a probe agent, which generates the probe packets which take a random walk in the network. Then we have the SDN controller, which adds the necessary forwarding rules to guide the probe packets. And finally, we have the collector, which helps in estimating the delay. So at first, the SDN controller adds a mirroring of the forwarding rule to guide the probe packets. Then the probe agent generates a probe packet, which reaches the switch S1. Here, S1 has the necessary rules to mirror the probe packet, and the mirrored probe packet reaches the collector. The collector, on arrival of the mirrored probe packet, notes a timestamp of arrival as T1. And simultaneously, the original probe packet makes its way to S2. And again, the probe packet is mirrored and sent to the collector, where it's timestamped again as T2. Now, the delay of the packet the delay experienced by the probe packet from traveling from S1 to S2 is nothing but the difference between T2 and T1. Now that we have seen how SDProber uses a probe packet to estimate delays on individual links, we'll see how SDProber guides these probe packets to a random walk. So for every probe packet, SDProber chooses the initial starting node randomly. And whenever a probe packet reaches a node, the next hop taken by the probe packet is also chosen randomly. So by altering the weight distribution, which governs how the initial node is selected, and also the weight distribution, which governs the next hop taken by the probe packet, SDProber can control how the probe packets go through the network. So this is very important because the system is able to adapt to changes in the probing constraints given by the network operator, and the system is also able to adapt to the changes in the network. Moreover, it reduces costs because the same probe packet can be used to conduct multiple measurements in the same network. So we implemented the random walk functionality using OpenFlow, and SDProber uses a mix of both forwarding rules and group tables to implement this. So the forwarding rule, the forwarding table over here helps to guide the different types of probe packets in the network. The group table in all mode helps in mirroring the probe packet. And finally, the group table in select mode helps in implementing the random walk. So let's take an example. So if a mirrored probe packet comes to a node, It matches a rule and gets forwarded to the collector. It's very important to distinguish a probe packet and a mirrored probe packet because you don't want to mirror an already mirrored probe packet. Otherwise, there's going to be an explosion of packets in the network. Now, if an actual probe packet comes through the node, it gets forwarded to the group table in all mode, where all the actions in the group table are implemented. So one of the actions is to mirror the probe packet and send it to the collector. And the other action is to forward it to the group table in select mode. The difference between the group table in select mode and all mode is that in select mode, only one action is implemented. And the action which is implemented is directly proportional to the weight which is associated with it. So if a higher weight is associated with an action, there's a higher probability that the particular action will be implemented. So in this example, this probe packet matches the first rule. Therefore, it gets forwarded to the port P1. Now, if another probe packet comes to the same node, it might actually match a different action. And this action could be forwarding to port PN. So it's very important that SDProber recalibrates its weights, that is the initial node weight selection and the weight distribution for the next hop, so that it could guide probe packets to regions where it's important. So we use this very simple binary exponential backoff technique to adjust the weights. So SDProber, based on the previous iteration, doubles the weights on links whose lower bound is not satisfied, so that more probe packets go there. And SDProber reduces the weights on links whose upper bound is already satisfied, so that the probe packet doesn't go to that particular region. So we evaluate SDProber using two competing approaches, which use the shortest path to send the probe packets. And in each of the technique, the probe packet is mirrored at every node, and the delay is calculated the same way as SDProber. The first technique is called a random pair selection, where pairs of source and destinations are randomly chosen, and a probe packet is sent through the shortest path between the source and the destination. Now, the second technique is a greedy path selection, where pairs of source and destinations are randomly chosen in such a way that the sum of the min rates of the unvisited links is maximum. So greedy path selection is very similar to random path selection, but the only difference is that greedy gives preference to source pair destination, which have more number of unvisited links. So we evaluated SDProber in Mininet using a topology from Topology Zoo, which consists of about 196 nodes with 243 links. This is the largest topology which is available. And we initiate a probing iteration every 30 seconds. So this means to say that SDProber recalibrates the weight every 30 seconds. And we evaluated all the three techniques using three different probing profiles, which is nothing but varying the lower bound and the upper bound, which is represented by min and max. And ideally, a network operator could actually choose a probing rate based on some historical measurements or based on certain SLA requirements for the customers. So at first, we show that SDProber has control over inspection. So the graph below shows this. The red line of the graph is the expected number of probe packets which is supposed to go through the links. And the blue line is the actual number of probe packets which is seen in our experiments. So we observed that the actual number of packets which is seen is about within 10% of the expected value. So this shows that SDProber has control over the random walk, and it could send probe packets where it's needed. Then finally, we show how effective SDProber is. So for each method, we increase the number of probes available for iteration till the min rate is satisfied. So this is nothing but we're making sure that there are enough probe packets available to satisfy the min rates for all the three techniques. The graph to the left shows that SDProber requires about 4 to 12 times less packets to satisfy all the min rates on all the links in the network. And while satisfying these min rates, we also observed how many times these approaches violate the upper bound constraints. The graph to the right shows this. And we see that SDProber sends 10 to 62 times fewer packets than the other two approaches. So by this, we're able to show that we're not violating the upper bound, but also satisfying the lower bound, which is the minimum number of probe packets or measurements which needs to be conducted on all the links. So in conclusion, I presented SDProber, which provides an efficient and flexible delay measurement technique in networks which have bounded constraints. SDProber uses probe packets to measure delays in the network. And the probe packets are guided in a random walk function where SDProber adjusts the weights to guide the probe packets in the network. Weights are adapted very frequently using a very simple technique of binary exponential backoff. We evaluated SDProber in a real-world topology and showed that SDProber has control of the probe packets, and it's also cost-effective. I hope I'm motivated enough to read the paper so that it'll be great. And if you can ask me questions right now, yeah, I have time. Yeah, finish right there. Thank you.